We are Team ME49. Our project is on automation of tuning cover preset fixture. Our faculty advisor is Professor Weber, and our industry sponsors are Mr. Weber and Mr. Bernhardt from Radio Frequency System.
To give a little background on our engineering problem, a lot of RF equipment requires the use of tuning covers, which have deep-drawn brass tuners set at specific heights, and it's those heights that manipulate the signal being passed through. So first, the tuners are roughly set using a preset fixture, which is a machined aluminum block with holes drilled and tapped. Screws are then inserted to the desired tuner height, and those screws act as a height restrictor. Once the preset fixture is complete with the screws inserted, the tuning cover is placed on top of the preset fixture and tuners are pushed in until they are stopped by the screw, and this is considered a roughly tuned board. Fine-tuning then occurs manually for each board. Where we're hoping that our machine will fit in is by inserting the screws to a very specific height, and as you can imagine, the more reliable the preset fixture, the better the rough tuning and the less time needed for fine-tuning. The goal of our project is to design and fabricate a machine that can place screws to a desired height for RFS. The overall purpose of this machine is to decrease the tuning time for radio frequency components in RFS's equipment. The intended deliverables were a functional machine that could set screws at a preset fixture at a rate of 30 seconds per screw. We do have a couple design restrictions, and that is we have a very small vertical tolerance of plus or minus 0.005 inches. The maximum preset size we'll have to consider is 16 by 16 by 1.25 inches, and we do need to be able to accommodate tuner heights that range from 0.4 to 1.25 inches.
Our machine needed to be able to position itself quickly and accurately to meet the project goals. To achieve this, we implemented a gantry system for the X and Y movement of the machine. Driven by ball screws coupled to high-torque motors, this design is a solution that is both operationally and cost-effective. As the components we used are commonly employed in systems that require precision movements, they are proven for this application and easy to do maintenance on if the need arises. In order to drive the screws down into the metal preset blocks, we have chosen to mount a stepper motor along a set of vertical linear rails. Enclosed within a C-beam mounted to the X and Y gantry, a separate motor will control the vertical movement via a nylon cable pulley. Using gravity to allow the bit to fall into place significantly simplifies our system, as we no longer have to worry about knowing the initial rotational position of the screw. Also mounted within the C-beam is a laser distance sensor, which will allow us to read the depth of the stepper motor and therefore the depth of the screw being driven. Our depth calculation equations require that the tuner reach the same depth that the bit does. In order to achieve this, we utilized set screws that have a larger bit diameter than the tuners. This way, the tuners would be able to slide into and seat in the screw drive. The set screws were also chosen large enough that the interior chamfer of the drive would not create a discrepancy between the bit and tuner depth, but not so large that the threaded holes could not be placed close enough together.
To improve compatibility with last year's senior design machine, this machine will run from an Arduino Mega microcontroller with a built-in script to take movement directions directly from a computer. On startup, the machine will run a code to self-orient and auto-home itself regardless of where it is before starting. This automatic movement negates the need for an HMI, simplifying the working process. Direct integration between this machine and a computer removes the need for a full human-machine interface and reduces the amount of user error within the system by interacting with the data directly. On the machine, there will be several LED lights to very clearly and concisely show the state of the machine as it is operating.
Our current status for this project is that all our critical hardware are installed and tested for basic functionality, and that include the X, Y, and Z movements. We also tested the structural components with the expected load on the machine and vibration condition to make sure we minimize the errors. Lastly, some of the components such as door, protective housing, LEDs were purchased, but we were not able to install due to the pandemic. However, those components will not affect the functionality of the machine. And as you can see from the picture on the right, this is our current machine build that has all the structural components finished, and with the motors and drivers, it can perform basic motion functions.